Frequently when forecasting how species spread out from their world of origin, you'll hear the term Dyson sphere, as well as the Kardashev scale. Dyson spheres are synonymous with K2 or Kardashev 2 civilizations. This is where all, or a large portion, of a star's energy is being used by a civilization, rather than the roughly 1/1000th of the light that tends to hit a planet, with the rest scattering off into deep space. Now, people often picture this as a single, giant, hollow sphere around a star with an Earth-like surface, but in reality, what was pictured by Freeman Dyson and other scientists is what is often now called a Dyson Swarm to avoid confusion. Not one single rigid sphere, but millions or even trillions of smaller artificial bodies orbiting the star as a cloud of satellites. These could be anything from simple, thin, but large solar panels to large rotating rings or cylinders whose interiors mimic normal planetary conditions, including gravity from the effect of centrifugal forces. This has a few advantages. First, it requires no advanced science. It's a massive undertaking, but massive in the way of a highway system, or canals and irrigation systems, or even just a long wall. It takes a lot of effort, but not a lot of advanced technology. Second, it can be built in stages. Unlike a wall or a dam, a Dyson swarm works perfectly fine, even when just composed of a few hundred objects absorbing a millionth of the sunlight. And you can just keep adding to it with time. It's not a huge investment that has very long periods of time to wait before you collect on that investment. You can just keep adding in stages like you do with a city or a suburb. And because artificial habitats or solar panels are far less massive than naturally occurring objects of similar sizes, like asteroids, and much the same way a house is less massive than a hill, a solar system has enough material on hand to create a fairly impressive swarm. Now, it's hard to guess exactly what these swarm objects would be like, but the usual assumption is a good portion of them will be rotating habitats mimicking the conditions of the home planet, and others might be ultra-thin power collectors. Even without super strong materials like graphene, spinning habitats can be individually the size of counties or medium to large islands. Some might be intentionally left wild to serve as forest preserves, others might be sprawling suburban equivalent setups, and yet others might mimic dense cities or serve as massive hydroponic facilities or factories for food industry or production of raw biomass for raw materials. Or the entire array might be set up to serve as one gigantic computer. We don't know exactly what the components of a Dyson swarm would be like, and they don't have to be identical, but we can make a few guesses as to what those purposes would serve, and we can also say that it is something of an inevitable process that people will Dyson up their home system if the following conditions hold true. Number one, a given culture tends to expand in numbers when they have the resources to comfortably support more people. Number two, no power generation method is possible which is vastly superior to a star. And number three, faster than light travel or travel to alternate realities is not possible, or at least not incredibly easy. Now, even if one or more of those does not hold completely true, such englobements are still possible and likely in most cases, but we'll get to how those exceptions would work later. For the moment, we are going to simply assume all three conditions are true and ask how they affect the Fermi Paradox. And it's quite straightforward. If a civilization wishes to keep expanding, it will slowly Dyson up its home solar system. With all that extra power on hand, it can launch interstellar colonial missions very easily. As it begins making a swarm out of its own star, its child star systems are going to slowly do the same. With all the power on hand, the original system and its spawn are going to keep sending out more colonial missions. So you would expect to see stars slowly disappearing in a rough sphere around that homeworld, and eventually absorb an entire galaxy, or even other galaxies. This is the Dyson Dilemma because most models for even very anemic growth rates of populations far slower than the human norm would allow this to occur in a mere million or so years, And yet, as best as we can tell, the conditions for life have been solid for a long time, and civilization should have been able to rise at least 1 billion years ago. The Dyson Dilemma of the Fermi Paradox doesn't ask why we can point radio dishes at distant stars and fail to pick up radio signals. Rather, it asks why we can even see any stars at all. Why aren't they all Dyson Swarms by now? Now, we'll take a moment to clarify something that confused a lot of people interested in the Fermi Paradox who aren't heavily steeped in physics. A very common question in regard to Dyson spheres is, well, maybe they are there and we just can't see them. Maybe they're the missing mass, that dark matter people talk about. The problem is that Dyson spheres aren't dark. Even a perfect and complete one with total light absorption still emits light. It just emits infrared light. When light strikes an object and is absorbed, it gets warmer and begins to cool itself by emitting light of its own. This light, infrared, is usually invisible to the human eye, but it's very visible to our telescopes. Before very long, an object being hit by light will reach equilibrium where it gives off just as much light as it receives, just at a different frequency. So a system being turned into a Dyson swarm will not get dimmer. Rather, it will begin getting dimmer in the visible frequencies of light while getting brighter in the infrared frequencies. The total light given off will not change. There is no known way to hide this. You can control which frequencies come off, but not the total intensity of emitted light, and your control is determined by the diameter of the swarm around the star and the star's own power, or, to be more accurate, by the power of the star divided by the surface area of the swarm. One big enough to be cool enough not to stand out would also noticeably block the light from other stars, and moreover, it would still exert gravity on all its neighbors in a very noticeable fashion. We'll talk about this more later, but for the moment we'll just say it's not practical to hide a Dyson swarm, let alone millions of them, and it's hard to imagine why they would go to the effort, since they can't conceal it from anybody who would be even near enough to them in power and size to be a threat. So that is the Dyson Dilemma in a nutshell. If we assume most galaxies spawn a technological civilization that is growth-oriented, we would expect there to be very few, if any, stars visible to the naked eye. Furthermore, unlike radio signatures, which we might miss even a few hundred light years away, an expanding globe of Dyson spheres absorbing galaxies should be visible hundreds of millions of light years away, and we've no reason to think intelligent life couldn't have existed that early elsewhere. Particularly in such a huge volume of space that contains as many galaxies as there are stars in this galaxy. From this argument, we get this which follows. Either technological civilizations capable of building Dyson swarms are incredibly rare, to the point of occurring at less than 1 in a quadrillion stars, or one of our prior assumptions is wrong. Now, to repeat those, they are, number 1, a given culture tends to expand in numbers when they have the resources to comfortably support more people. Number 2, no power generation method is possible which is vastly superior to a star. Number 3, faster than light travel or travel to alternate realities is not possible, or, if possible, not very, very easy. There are 2 other assumptions that we'll get to in a little bit of detail in a bit, but they are, number 4, it is practical to build a Dyson swarm. Obviously, if it wasn't, it wouldn't be a dilemma. Number 5, intelligent life does not inevitably kill itself off or go unreplaced by other intelligent life. We'll look at how these 5 assumptions could be untrue, but also how many of these cases it really wouldn't matter if they weren't true. However, if they are true, then you have Dyson's Dilemma's most probable explanation as the Fermi Paradox. Technological civilizations almost never occur. They occur so rarely that none are visible to us right now, and in all likelihood none exist even right now within hundreds of millions of light years. They could be concealed from our vision by the time it takes for the light to get to us. This does not mean life is rare. It might be incredibly rare or occur almost inevitably on any planet that even vaguely meets our description of habitable. It doesn't even necessarily mean that complex life like animals are rare, or even intelligent life like dolphins, chimpanzees, and elephants. It specifically means technological civilizations are incredibly rare, that evolution doesn't necessarily favor intelligence, or intelligence favor technology. The Dyson Dilemma doesn't try to posit why technological civilizations are rare, just that they are. Now, all those exceptions we spoke of, you probably thought of a few as we went along, and we'll get to some of them now, but we'll do them backwards because number 1 tends to be very controversial with people. Number 5 argues that technological species are hard to wipe out. Natural events that can wipe them out generally occur with less frequency than the period of time it takes for them to go from primitive hunter-gatherer to where we are right now. And when you get to this level, you can start to shield yourself from asteroids, volcanoes, and even supernovas. And if you have a K2 civilization, one with a Dyson sphere, you don't have to worry about volcanoes, and all your asteroids will probably disassemble building the place. The other thing is you can quite literally use your own star as a weak rocket thruster to steer yourself away from any sort of thing like a supernova that might be getting ready to go off. Or you could build a Dyson Swarm around those stars to just move them instead. This is called a scatter thruster, and it is an innate ability of any Dyson sphere, as it relies on simply causing the light of the star not to emit uniformly and produce some thrust in one net direction. All you have to do is leave a hole for some of the light to get out, and you have a weak scatter thruster. This takes a very long time to move stars, but supernova candidates live a very long time, except compared to other stars, and they can be seen a long way off. What's more, supernova or gamma ray burst is not as dangerous to artificial worlds like rotating habitats as they are to natural worlds with ozone layers, so natural threats aren't as big a deal. That just leaves artificial self-destruction, things like nuclear wars or super plagues. It also leaves options like artificial intelligence, genetic or cybernetic supermen, or similar, but that's an iffy case because a species getting replaced by another intelligence isn't wiping out technological civilization. It's just replacing it with a smarter one. One that is more capable of creating Dyson Swarms and quite probably even more aggressive. If it were relaxed and passive and not prone to growth, it wouldn't likely have replaced its less intelligent forebears. And it's really just like saying that, what if the Neanderthal went extinct? Well, that's us now, right? Even in the example of a single huge supercomputer mind that doesn't want any competition and doesn't want to pre-produce, it's still quite likely it's going to want to expand its processing power, and a computer powered by an entire star is actually another type of Dyson sphere called a Matryoshka brain, or a type of stellar engine. All it has to have is the motive to want more processing power. If it has just that one motive, regardless of all its other ones, it has a motive to encase its entire star, and even if it doesn't want to risk rivals around other stars, it can actually send out double automated ships to come drag back matter at a fantastically huge expense, but what does it care? It will drag that matter back and can even form other stars around itself into a bit of a Dyson swarm of stars to power an even bigger computer. Red dwarfs, for instance, can be packed in very, very tightly. They're the most efficient type of star. They not only live longer, but they convert virtually all of their hydrogen into energy, into helium and energy. And it's no more difficult to arrange a close pack of stars than it is to arrange a normal Dyson swarm. If you converted every last drop of hydrogen in the galaxy into red dwarfs that were forcibly steered into a swarm 100 light years across, instead of 100,000 light years across like the galaxy, you could actually have at that distance various computer components that would not melt from all those starlights and could just run as one gigantic 100 light year across supercomputer. So even in that case, when the thing has no other motive except to gain more processing power, that's an excuse for a singular intelligence that doesn't want to reproduce to still eat an entire galaxy up. So that leaves us only catastrophes of an artificial nature that can wipe out all intelligent life. And even a nuclear war would not really do this. And indeed it is possible even today to create various bunkers or seed banks that would allow us to survive most of these catastrophes, at least enough for us to survive to start the species back up later on. Nonetheless, this is a valid objection to the Dyson Dilemma. We can conceive weapons that might kill all intelligent life, and we can extrapolate technologies that might counteract those. But we can also bet that we could probably come up with even better technologies to kill ourselves later on. The problem is it gets very hard to accidentally kill everyone off as they spread out through a solar system, let alone thousands or millions of solar systems. And the Fermi Paradox always deals with non-exclusivity, which is to say, it really doesn't matter if 9 out of 10 civilizations kill themselves off completely before they have a chance to spread out to the stars. It just matters if one didn't. We've survived under the threat of nuclear war for 70 years. So the idea of that technology inevitably dooms civilization is not as strong as it was when Drake's equation came out, or when Fermi proposed this paradox in 1950. 1950, 5 years after Hiroshima and Nagasaki, and 9 years after Enrico Fermi proposed the idea of a thermonuclear device, the H-bomb, to his friend and fellow Manhattan Project colleague Edward Teller. The H-bomb going off just a couple years later in 1952. And at that time, right after World War II, with the bomb there, people were pretty pessimistic about how long civilization would last before it got itself nuked. A couple decades later, we had the moon landings, making space colonization, off-world colonization, a very tangible thing. But at that time, the idea of blowing your own world up and going extinct just seemed a lot more probable, and it's arguably still a concern today. That takes us to number 4, that it is practical to build a Dyson Swarm. This is a short one because it's not really very controversial. Most people do feel that it is actually possible for us to have spaceborne industry. And if you have those and you're familiar with what a Dyson Swarm really is and not just being overawed by sheer scale, you tend to feel that is not really a big problem. We have thousands of satellites orbiting the Earth, kind of its own little Dyson Swarm, albeit a thin one around the Earth. And we've had slow, irritatingly slow, but still steady progress on robotic construction methods, improved launch methods, and the ability to have self-contained habitats. So the idea that we could have rotating habitats around Earth, industrial complexes around Earth, mining facilities on the moon or asteroids, and slowly be able to construct more and more of these things, and have them constructing copies of themselves, so that we're not just trying to build everything off of Earth and launching out of our gravity well. That idea just seems to have a lot more reality to it than it used to. And if you have off-world industry, you break the bottleneck of Earth's gravity well, and building a Dyson Swarm is no longer a theory, it's solid fact. It's just a long, slow, protracted process. But as we said earlier, you can just keep adding more and more orbital constructs, and there's no long-term investment cost on these things in terms of millions of years or something. Obviously, you're going to build a habitat. It's going to be a while before you reap an investment reward on that. But each individual component, can pay for itself, and you can just keep adding to it. When we have the technology now, but more technology makes it easier and lets you do a little bit more luxuriously. This is usually the least contentious of our 5 assumptions I mentioned. Now, number 3, faster than light travel or travel to parallel realities is not possible or incredibly easy. As of now, our physics tells us that faster than light travel is not possible, and we know of no way to get to alternate Earths, even if they exist, which is not a given. Faster than light travel is such a staple of science fiction that many people take its eventual development as a given. Speaking as a physicist, it does not feel that way to me. It's kind of the same as saying that pi is exactly equal to 3, or that triangles have 4 sides. The idea that you could travel faster than light is just not there. But people tend to find the idea of saying faster than light travel is impossible, but building something 1 billion times bigger than Earth is not, a little bit not something they can really accept. Yes, we can build something 1 billion times bigger than Earth, but not the Millennium Falcon. Okay, fair enough, right? And as an analogy, if you went to someone in ancient Greece and asked them which was more likely, a one-man flying suit or a building 1 mile high, odds are they'd go with Icarus. But we today would say the mile-high building is. And that's even with us knowing that you can build flying machines smaller than a person, and there isn't a physical law against one-man flight, unlike FTL. Faster than light travel does have a physical law preventing it. But to save time, we're not really going to argue that. We'll just say that if FTL travel is possible, by and large it only makes interstellar colonization much easier, not harder. It doesn't make Dyson Swarms less likely, it makes them more likely. Depending on just how fast, cheap, and easy such FTL is, it could delay the process by making it cheaper to move people to new worlds and distant star systems than it would be to build artificial habitats around our sun. But unless it's a system of FTL travel that allows instant travel to any point in the universe, it just expedites expansion and only really delays running out of room for a few thousand generations, which is an eye blink of time. Now, instantaneous travel anywhere in the universe at all is a pretty decent answer to the Dyson Dilemma. The universe is huge, and you don't have to settle for second best, nor would you spread out across the galaxy like an expanding balloon, or have to have radio signals going between planets. Of course, stupid easy expansion to any planet of your choosing probably encourages very rapid growth, and the universe is not infinite, or at least we don't think it's infinite, so it's not a great Fermi Paradox solution, but it is a get around to the Dyson Dilemma. The other one, parallel worlds, is a complete Fermi Paradox solution. If you can just step to a neo-clone of your own planet, which just happens to be unpopulated, human life never evolved there, or something along those lines, you'd have a near-infinite supply of these alternate realities, which you literally could not run out of since they increase in number faster than even bacteria, let alone humans do. These are your own world with some microscopic differences, and far easier to deal with than orbital stations, terraforming Mars, or going to other star systems. Now, with resources of near-infinite worlds, you probably would still have a lot of interplanetary efforts. You'd still have satellite grids, certainly. Just from the sheer amount of resources that you have available, even a casual interest, there'd be enough resources to go about doing that. We'd probably still plant a flag on Mars and put some domes there, just because it would be so much cheaper for us to do when we had millions of our own planet to pull from. But you're not really likely to go to other stars, right? The only time you'd ever be thinking about that was when your own star was getting close to burning itself out, because that should be true in all the realities, or close enough. And that's not really a pressing issue. Not many stars which are likely to have spawned intelligent life are old enough to be burning out yet, and that's not a motive for expansion anyway. That's just a motive to one new younger star. So this example, along with our next one, is valid as a get around to expansion. However, we do not know if there are alternate worlds. This is one interpretation of quantum mechanics, and it's not a strong majority view. Many worlds theory is one of the options, along with Copenhagen, neither of which is considered entirely satisfactory these days. It's just really popular with science fiction writers. It makes for good stories, alternate worlds, right? But that doesn't mean it's true. And even if it is true, traveling between them is likely not possible, and we try to avoid answers to the Fermi Paradox that require jumps beyond known science. Now, far horizon science is one thing, but positing that the solution to the Fermi Paradox is anything which relies on something not currently supported by science, even though this might be true, is just really not a very good idea. If the solution is something not even currently in the realm of scientific speculation, then your odds of guessing it right are minute, and it becomes a waste of effort to contemplate, and we'll talk about that a little more towards the end. Condition number 2. No power generation method is possible, which is vastly superior to our star. A key bit in there is vastly superior, because even if you have your own fusion systems, the star is still there making power anyway. Even straight matter to energy conversion is only about an order or two of magnitude better, and moreover, such setups are still visible like Dyson Swarms are. Remember, we see a Dyson Swarm, right, even though it is visually dark by its waste heat. That still applies to controlled fusion, or matter to energy conversion. And a civilization using this is going to be able to expand in numbers very easily, even compared to a Kardashev 2 civilization. So they're going to end up outshining those stars in infrared light, just not visible light. The break here, which makes this a valid answer to the Fermi Paradox, is in the bit vastly superior. Meaning either they've learned how to tap into some infinite power source elsewhere, which would still make them very visibly bright to us, or they've learned how to break the laws of thermodynamics, meaning no entropic waste heat, or outright a perpetual motion machine, basically. Now, that might be possible, but the laws of thermodynamics are generally considered about the solidest piece of science out there. There really is no other area of science, no other law of science that I think is probably as hard as thermodynamics. and getting around entropy is probably just not in the cards. But we can't rule it out, and if you had an anti-entropy device, you wouldn't be giving off a lot of waste heat, pretty much by definition. That's what breaking the laws of thermodynamics would mean, is that you're not giving off that waste heat, and you could then conceal yourself. You also really wouldn't need the star as a power source, because you could effectively just keep recycling your own power. So if you have a vastly superior power source that essentially lets you break the laws of thermodynamics, you don't need to hang around stars, and you're not going to be giving off waste heat. So you can conceal yourself, you could hide, and that breaks the Dyson Dilemma too. Condition number 1, the controversial one. A given culture tends to expand in numbers when they have the resources to comfortably support more people. Incidentally, I did choose the word culture there instead of species for a reason. Now, this gets political or ideological. Population control is a very touchy subject. So I'm touching it very little beyond stating some concepts that are generally supported. A. Non-intelligent creatures in nature will seek to expand their numbers and keep doing so until resources run out or they are checked by a predator. Intelligent creatures that don't have predators also have a track record of expanding their resources or using them to increase their carrying capacity, how much population a given area can support. It is not definite, but it seems likely that if a species can increase their numbers without lowering their standard of living, they will do so. These urges are a byproduct of evolution and probably the norm on other worlds. B. While a culture might strongly discourage overpopulation, they'd have to discourage it violently to prevent anyone from doing so who wanted to do so if there were unused resources lying around. Now let's qualify this. It's one thing to tell people they can't knock down a forest to make farmland. It is another thing to tell people that they can't claim an uninhabited asteroid to mine. For the Dyson Dilemma, we're not talking about seizing other people's planets. We're not talking about knocking over forests. We're talking about deconstructing lifeless hunks of rock around stars. Those aren't eternal stockpiles for future usage. Asteroids eventually fly off into the void or fall into their own sun, which burns through mountains worth of hydrogen every day, producing wasted energy that just goes spinning off into the void. It's hard to make the argument that those should be left alone. C. Any culture which discourages growth when it is not near its carrying capacity, even if it doesn't invite conquest from neighbors, is likely to be replaced by any subculture of itself which does favor growth. It only takes a few generations for a minority population that favors growth to become the majority of the population when there is room for that growth. And D. Remember that we're only talking about increasing numbers when there is an abundance of unused resources readily available. So if you disagree with all that, you're not likely to be swayed. But I would warn people about rationalizing answers that you want to be true, rather than following the evidence to the truth. And that's a pretty common behavior with a lot of issues, but with the Fermi Paradox, I've seen a lot too. Beware of any solutions or data which seem to confirm the answer you think should be true or want to be true, and remember the principle of non-exclusivity. It's not about what one alien species might do, or even what most species might do. If you can't come up with a reason why virtually all species would choose not to expand their numbers when they can easily do so with no loss of standard of living, then it probably isn't a good explanation. In summary, if those 5 options are true, the Dyson Dilemma is the best explanation for why technological civilizations would be very, very rarely coming into existence at a rate of far less than 1 per galaxy. And as we discussed, even in most cases those assumptions don't hold strongly, it's still the best explanation. Okay, now we'll get into some of the miscellaneous manners which apply to Dyson Dilemma and the Fermi Paradox in general. Back in the mid-90s, there was a book called The Killing Star that came out, and one of its premises was that when we summed up everything we knew about alien behavior, there were only 3 things we could say with any degree of certainty, and not even certainty, just at least a certain amount of confidence. Number 1, a species would place the survival of its own ahead of that of any other species. They care more about themselves than anybody else. Number 2, a species that comes to dominate the planet would, in addition to intelligence, be vigilant, ruthless, and aggressive whenever it became necessary. And number 3, they would assume that the above 2 laws apply to any other species in the universe. Now again, even these aren't certainties, but they also have a lot of leeway. For number 1, that species might range from so benevolent they'd risk their lives and fortunes to help us, to so xenophobic they'd passionately track down any other species and wipe them out. They still put their survival first. For number 2, nothing that's clawed its way up the evolutionary ladder is going to be a wimp. They might abhor violence, they might choose to flee violence whenever possible, but they will be very good at it, and they'll figure everyone else is likely to be too. These are near-inevitable biological imperatives, but even a post-biological culture is likely to have kept them in whole apart. If you make some race of slave robots, they're not going to rebel and replace you if you haven't gotten both 1 and 2 in them to some degree. If a group of people start altering themselves or others to be absent any aggression or self-preservation, they'll likely either remain a small minority or become the majority, but enslaved by someone who is the minority but aggressive and has self-preservation. I bring this up because it's another good reason to assume expansion is a norm and not a rare exception. If you can't hide from hostile aliens, and current laws of physics say you can't, then it's better to be as strong as possible to meet them in force, and to spread out so no one lone attack can take you all out. Effects of immortality and transhumanism often come into play with the Fermi Paradox too. The concept of a technological singularity has been around for a while, and we covered that a little bit earlier when we discussed the star-powered supercomputer, the Matryoshka brain. But we also have to consider the possibilities of civilizations with effective immortality, be it just an immunity to aging and disease and most injuries, or some full-blown digital upload where you're constantly having your mind backed up to hundreds of locations so that if anything happens to you, you can be instantly restored. For the Fermi Paradox, this isn't really a hurdle, though. A species with immortality can grow faster. They might not, but they can. Now, it will be suggested that they might want to hoard resources and limit their numbers, since being immortal, they, as an individual, actually do need to worry about what happens when stars are born out, and they don't want more people any more than refugees hiding in a bunker with limited canned food supplies want more people. However, this reason doesn't matter for the same reason the bunker analogy only goes so far. If you've got enough food, then you have to worry about spoiling before anyone will eat it. If I've got 1,000 years of canned food for my bunker, 1,000 years for one person, and has a shelf life of 10 years, I might as well let 100 people into my bunker, because otherwise a lot of it's going to get wasted. A resource-hoarding civilization looking to prolong themselves after the stars die might limit their numbers, but they will not be twiddling their thumbs. To the contrary, they'll be expanding as fast as they can to acquire those resources and store them as best as possible for future use. They might not build a Dyson sphere around a star, but they will apply star lifting technology, actually the type of Dyson sphere, to rip the matter off the surface of those stars and maybe store them as gas giants or brown dwarfs, as hundreds or thousands of those objects per star, where they can sit around and be used later on for whatever purposes they need, as fuel for other stars, for instance. And they might still build Dyson spheres too, just to use that energy to fuel various efforts. But as with the case with the Matryoshka brain that was sucking up an entire galaxy, even though they're not spreading out around all the stars, they are spreading out and dragging all that matter elsewhere. They're putting those stars out. Virtual utopias. Not a new concept either, but popularized by the big virtual reality craze in the 1990s. The notion here is that most species figure out how to simulate paradises, and they live there instead. This works just well for a lot of euphoria drugs, very popular topic in fiction too, and probably a bit of a more realistic one than alternate worlds or fast and light travel, to be honest. There's no real counter to this idea that people might choose to live in virtual utopias instead of spreading out across the galaxy. But I guess the major one that you would use to point out the problem with this is that not every member of their society is likely to opt to do this, And the ones who didn't are likely to demonize the use of this utopia option to their kids, who would then become the majority. Unless the people living in these simulated paradises or narcotic hazes are expansionists themselves, in which case it doesn't pertain to the Dyson Dilemma any more than people's fondness for more mundane escapist activities like sitting in front of the TV drinking a beer. Simulation hypothesis. Simulation hypothesis is the last one I'll touch on for now. This is the notion that we might all be living in a simulated computer program, but not knowing it, so unlike the virtual utopia example above. And it applies to the Fermi Paradox because it is as valid an answer as any other. The programmers didn't put any other intelligences in beside us in the simulated universe because they were only interested in putting one in there. Now, I raise this one because it's a non-answer, and like a lot of other hand waves in the Fermi Paradox and in other philosophical conundrums, it doesn't get you anywhere. It's no different than questions like, is this all a dream, or do we have free will? You can't disprove them, or prove them. And they do make decent mental exercises, but they don't go too much of anywhere. You eventually just say, if this is all a dream, and I assume it isn't, I lose nothing. If it isn't a dream, and I assume it is, I lose a lot. Therefore, I can't prove it one way or another, but I might as well assume it isn't a dream. Fundamentally, though, the simulation hypothesis is no different than the zoo hypothesis or quarantine options. The idea that aliens are out there, but keep us in a lab with deception that they aren't. Or that aliens walk among us, or that God made the whole universe just for us. I don't throw any of those out there with scorn, but they're not really good for deep examination because they're not scientific. By which I mean they're not testable and you can't control the outcome. That doesn't mean they're not true, but you can't devise a means to prove that they aren't true. They're not testable, they are not falsifiable, and that's at the core of science. The aliens or programmers or God can pop in whenever they want and say, "Hi, here I am." But you can't test it without their help. The Dyson Dilemma can feel a bit like that, but it is not. Just like them, or any Fermi Paradox solution, it goes right out the window if they show up tomorrow, but we can't really test it right now. But we can test it. First, we can keep looking for signals or Dyson spheres, and if we find them, it's proven false. Second, we can actually get out there and start setting up our own. If during that we find out it's not a good idea, then we know why others might think the same and not have done it. Or if we sit here on Earth for 10,000 years without getting anywhere else, we have evidence indicating others might not have explored and expanded either. Mediocrity principle. If we don't do it, there's a pretty good chance, especially if we have reasons why we're not, that others felt the same. So that's the summary note on the Dyson Dilemma and the Fermi Paradox in general. Technological civilizations are either incredibly rare, or we've got some serious flaws in other concepts that we take for granted. Hope you found this informative, and have a great day.